Okay, so I guess we can start. So my plan is to go by the order of papers that we see on the schedule, unless some problems occur. So welcome to session C1 and ICALP. So do we have Moran Nehushtan?
Yes.
Great. Would you like to share? Yes, we hear you well. You're welcome to share your screen.
Okay.
Moran will tell us about simplifying and unifying replacement paths algorithms and weighted direction graphs.
Okay. Can you see the presentation? Yes. Can you see the? Okay.
Yep.
So how much time I have? 2 minutes?
Roughly.
Okay. So in the replacement path problem, so first of all, my name is Moran Nehushtan, and this is a joint work with Shiri Chechik, and the name of the problem is the replacement path problem. So basically, it's a very classic problem. You have a graph G and the shortest path P connecting two nodes, S and T. And the goal is to compute for every edge in the path, the distance from the source to the target in the graph G minus C. In other words, you need to cope with the deletion of one edge. So this is a very known problem. And we've been able to tackle two variants. The first one is the M variant, where you are given a directed graph with integer edge weights between -m to m. And we assume that the graph doesn't contain negative cycles. And the second variant is the planar variant, where we are given planar directed graph with no negative edge weights. So basically, if you look at the state-of-the-art results in this table, so in lines 5 to 7, we cover the M variant, and in lines 8 to 11, we cover the planar variant. And as you can see by the running time, both of them, in the both variants, we have the state-of-the-art running time. Yet, the two problems were solved separately in different papers, and we've accomplished a solution that is very simple and that is cover both of them. Almost the same solution cover the two variants in the state-of-the-art running time. That's it. If you do consider polylogarithmic factors, so in the M variant, we improve the state-of-the-art by log to the power of 6. But the main contribution is that it's a very simple solution that combines, that uniformly solve the two problems. That's it. You want me to?
Thanks. Are there any questions to Moran?
I can expand a little bit behind what was given in the video.
Sure, shortly.
Okay, just in. Okay, so I suppose to that you are all seen the video, or should I? Okay, so just say a few words that I didn't say in the YouTube video. So basically what we have shown is a mapping from the graph G to a new graph. And this transformation is invertible and also the inverse of itself. Therefore, we've shown that the replacement path problem is equivalent to a new problem where you need to compute shortest cycles for all edges in the shortest path. So even if the algorithm will be break, in one of the variants. So this reduction will stay forever. And so also in the video, I didn't cover the passes. What if you want to return the passes as well, and not only the distances? And that's also possible because the problem that the algorithms that we reduce our problem to can return the passes as well. In the M variant, Euster and Zwick distance oracle can return the passes in a linear time. And in the MSSP problem, Klein algorithm can almost return the pass in linear time. It pays another factor of log the maximal degree. And if you want to cope with vertex failures instead of edge failures, then there is a simple reduction, at least for the non-planar case. In the M variant, you can use the reduction of replacing every node V with two nodes, like in the picture. And then if you want to cope with a failure of a vertex V, you can delete the edge that connects V in to V out. And that's it. If you have any more questions.
Is this, are these complexities tight?
So we don't have a lower bounds for the two problem. Maybe the replacement pass for the planar graphs can be solved in linear time. We don't know. For the M variant, the running time that we have, here it's basically dominant by one pre-process of the graph. So we don't believe it's possible, but we don't have a lower bound for this problem.
Are there any further questions?
I was just wondering what in the planar case causes this log n. Is this like one particular point or one particular data structure, or is it like pervasive throughout the algorithm that this log n is there?
Okay, so basically we reduce the problem of the replacement pass problem to a new problem, where we use the MSSP algorithm. Maybe I will show a simple. Okay, so basically we've been able to reduce the replacement pass problem to a new problem, the MSSP problem, and this is the bottleneck of the algorithm. The MSSP algorithm enables us to solve queries, to ask a few queries where all the sources share the same face.
Right. So if the graph were unweighted planar, then you can do it in linear time. But I think that was already known.
This is unweighted and unweighted planar.
No. It's just because MSSP runs in linear time for that.
In linear time for unweighted?
For unweighted, yeah.
Really?
But I think there was a separate work that already showed that replacement paths, if I'm not mistaken, that in unweighted planar graphs it already works in linear time.
Okay, I'm not sure if I have it. I do know that in undirected graphs, also in non-planar graphs, it can be solved in almost linear time. Depends on the.
What's the log n?
Yeah, so I'm not sure if I write it. Yeah, so in the word RAM model, you can solve even the undirected graph in M alpha time, but I'm pretty sure that, okay, if you say that there is for a planar graph and unweighted linear time MSSP algorithm, then it can also be solved but you said that it was already known.
Yeah, I think it was known by other techniques. Yeah, and maybe related to the question, the MSSP, there's a low bound for MSSP of n log n, but it does not apply to this problem. So,
right. Exactly. I can explain in another 2 minutes the main idea of the algorithm of the solution, that this is our that wasn't known before. Yeah. So okay. See, this slide cover the basic idea. I can explain it in like 2 minutes if you want. And the basic idea of the algorithm, which is really simple. So if you look at the path P that connects S to T, and you imagine a detour that goes from Vi to Vj, then if we flip the orientation of every edge in the path P, then we get a cycle that is composed of the detour D and the part that is skipped by D. So we get a cycle. This is the first observation. The second observation is that if you consider some edge E in the path P and a detour that is skipping E, so basically what you want to minimize is the weight of the replacement path, which is the weight of the prefix plus the weight of the suffix plus the weight of the detour. Now, the weight of the prefix plus the weight of the suffix is equal to the weight of the whole path minus the weight of the part that is skipped. So this is the second equation. And now the weight of the path P is fixed because P is fixed in our problem. So basically, if you want to find a detour that minimizes the weight of the replacement path, it's equivalent to find a detour that minimizes the weight of D minus the weight of S of D. So if we combine the two observations together, then we can replace every edge with a new edge in the other direction. And also to negate the weight of every edge in the path. And then the weight of the cycle becomes what we are actually trying to minimize. So it requires some details, but so basically this trick of flipping the edge, the orientation and the sign of the weights enable us to solve the problem with the ability of finding for every edge the minimal weight cycle that contain that edge. And in the two variants, the M variant and the planar variant, it's very easy to do so, to find a cycle that contain a minimal cycle that contain an edge for every edge in the path P. So this is basically the trick that enables us to solve the two problems, the two variants.
Okay. Is there another maybe quick questions, or we can sorry, or we can take additional questions also on the Slack channel? Okay, so thank you, Juan.
Thank you. Thank you very much.
Zihan Tan, you're not sharing your screen anymore. So you can share your screen, please.
Sure.
And Zihan will tell us about packing low diameter spanning trees.
You see my screen?
Yes.
Oh, okay. So I am Zihan Tan from University of Chicago, and I'm going to present my my paper on packing low diameter spanning trees with Julia Chuzhou and Mira Potter. So in this paper, we'll be studying the spanning tree packing. So so specifically, a spanning tree packing is basically a set of spanning trees in a given graph. And when we say packing, we usually means a set of objects that is disjoint in some sense. But here, we're allowing a slight relaxation in the sense that we allow the spanning trees to overlap a little bit. So we will be studying the following 3 measures of a set of spanning trees in the given graph. The first is size, which is basically the number of spanning trees in the packing. The second is diameter, which is the maximum diameter over all trees in the packing. And third is a congestion, is the maximum appearance of an edge. Basically, if we say that a packing has congestion C, then it means that for every edge, it appears in at most C of the trees in the spanning tree packing. Okay, so basically, if you want a graph to contain K spanning trees, disjoint spanning trees, then the graph has to be K edge connected. So in this work, we basically consider the case that if we are given a K edge connected graph, what kind of spanning tree packing can we find? So our result is summarized in the following table. The first line is the previous result by Tutt and Nash-Williams. They said that they proved that in a K edge connected graph, there exists, and actually there's an algorithm that can find K/2 edge disjoint spanning trees. There is a problem with this theorem. So this theorem is correct, but it doesn't say anything about the diameter. And when we want to apply this kind of spanning tree packing results to the distributed problems, we need the diameter to be small. So our result is the second to the 5th rows. So the first result is that we prove that every K edge connected graph with diameter D, there exists a K/n spanning tree packing that is disjoint, and each has diameter at most K⁴ The second is we can find a packing of K/2 spanning trees, and that cause congestion 2 with diameter at most K⁴ each. So we may wonder, so there is a exponential improvement between the diameter in the congestion 1 and congestion 2 case. So we may wonder if, what if we allow some more congestion, like a larger constant? And in the third line, we show that this is almost tight. So this is basically the best we can do. So if we are going to find a set of K/α spanning trees that causes congestion at most mu, then there has to be at least one spanning tree with diameter at least K/α_d mu to the d. Note that by scaling the results in our second row, we will get K/α mu to the d as an upper bound on the diameter. So this shows that when d is small, this is basically tight. And lastly, we consider a special case where a graph is KD connected. Specifically, if for every pair of vertices, there exist K edge disjoint paths connecting them, and each has length at most d, then we say that the graph is KD connected. In this case, the packing result is much stronger. So we can find a set of spanning trees, K spanning trees with congestion log n, and each has diameter at most d log n. So there's no exponential dependence on d. So this summarizes our results, and just briefly mention the applications in distributed computation. So we consider some problems in congest model. So the main application of our spanning tree packing result in the congest model is that it gives improved round complexities for many graph theoretic problems in a high edge connected graph with small diameter. For example, minimum spanning tree, global mean cut, and ST shortest path. So this improves the round complexity on the compared with the general graph, which is d plus √n that is tight. And also a generalized construction of a secure distributed algorithm, and it gives the first algorithm for information dissemination problem, approximation verification of edge connectivity, and also provides the first separation between hardness of MST and global mean cut, which are more or less considered to be equivalent in some other general graphs, for example. So that's all. Thank you.
Thank you. Any questions? Can you say about this separation between MST and min cut?
So yeah, so the result is a little bit detailed. You can probably look at our paper in the application section. So basically, there's a separation between the round complexity. We provide a round complexity for both problems, and a lower bound on one of them, which separates it from another round complexity.
This is in the congest model?
Yes. But we require the graph to be high edge connected and has small diameter.
Okay.
You also mentioned that your results are algorithmic.
Yes.
What is the running time of these algorithms?
For the second row, third row, and fourth row, the algorithm is very fast. And the algorithm is actually very simple. It's basically for each edge with probability 1 over k, or 1 over k over 2, or 1 over k over alpha, depends on the number of spanning trees you want. Keep this edge. And with probability 1 minus this, throw it away. For each spanning tree, we does this, and we repeat this process for a certain number of times, and we get spanning tree. So specifically, each spanning tree, each edge of the original graph, uniformly at random choose a spanning tree to go to, and that's all.
More questions? Okay, thank you very much.
Thank you.
Next speaker is Pavel.
Hello.
Hi. So please feel free to share your screen.
Yes.
And Pavel will tell us about minimum cut in order of m log² and time. And let me just mention that this is the best paper award for track A for this ICALP. So congratulations.
Okay, thank you. Can you hear me and can you see my screen?
Yes.
Can you see my mouse as well? Or?
Yes. Mm-hmm.
Okay, great. So, hello everyone. This is joint work with Shai Moses and Torin Weiman, and I'm Paweł Gawrychowski. And it's about faster algorithm for the minimum cut problem. So I will spend a few minutes explaining the main result in this paper, and then I'm happy to answer your questions. So probably you all know this problem, but just to be sure, we are given undirected edge-weighted graph, and the weights are positive, but they could be real numbers. It's not really important for integers. So m is the number of edges, n is the number of nodes, and now we want to partition the nodes into two proper subsets, non-empty S and non-empty complement of S. And the goal is to minimize the total weight of all blue edges with one endpoint in S and the other endpoint not in S. And the graph, there are no assumptions on the graph. So just the figure might suggest something, but there are no assumptions. It's a general undirected edge-weighted graph. Okay, and we are mostly interested in the sparse case. So we want the time complexity to depend mostly on the number of edges m. And the main result in our paper is that now we have an algorithm that can solve this problem in m log² n time with high probability. So it's a Monte Carlo algorithm. There is a small probability of returning an incorrect answer. So what's the high-level idea of this algorithm? So in '96, Karger gave this very nice algorithm for the same problem, working in m log to the power of 3n, so we shave 1 log. And he introduced this framework based on random sampling and tree packing that has been mentioned in the previous talk. So we operate on the same framework. I will not show you the details, so please see the paper on the log talk. The bottom line is that he was able to reduce the problem into log(n) instances of a more structured problem, in which we are given some kind of hint about the structure of the min cut that you seek. And this hint is just a spanning tree T. So you are given graph G and a spanning tree T of G. And now your goal is to find minimum cut crossed by 2 of the edges of T. So you want to select 2 edges of T, those blue edges, E and T prime. And when you remove them from T, you obtain, well, in this case, 3 components. So this middle part becomes S, and the other nodes are outside of S. So you choose 2 edges and they determine the partition of the nodes into 2 sets. And you want to choose those edges as to minimize the cost of the cut. So Karger was able to solve this subproblem in deterministic m log² n time, and because there are log(n) instances, he obtained his result. And our main technical contribution is that actually you can solve this subproblem in m log n time deterministically. So then it's m log² n time. There are some technical details. I mean, we had to redo this reduction to also work in m log² n time. It was not important for Karger's result. So let me just show you briefly how we solve this problem. So it turns out that there are 2 cases, and the more difficult case is as in the figure. So you have T, you root T in arbitrary node, And then let's assume that E and E prime are independent. And you can see in the figure what I mean by independent. So E is not ancestor of E prime. Okay, so we have two steps. In the first step, we reduce this case to multiple instances of total size O of M of some other problem. And the reduction takes M log n time. And then the second step is that we show how to solve an instance of size S of this new problem in S log S time. So when you combine those two steps, you obtain M log n. And this new problem, we call it the bipartite problem. So it's a problem on two trees. We are given two trees, T1 and T2. And additionally, you have a number of cross edges, those green edges, join nodes from different trees. And each of the green edges has a cost or weight, and also each edge of T1 and T2 has a cost. So now the goal is to choose one edge from T1, one edge from T2, and we want to minimize the sum of the costs of E and E prime minus the total weight of all cross edges in the subtrees of E and E prime. Those are the green edges in the picture. Okay, so this is the subproblem, and we came up with some kind of divide and conquer algorithm that can solve this in S log S time, where S is the number of edges and the size of the both trees. Okay, just to conclude, I will show you the table with some of the results. It's not a complete table, so if your result is not here, I apologize. Those are just the most relevant results to this talk. So now we have this M log² n for general graphs, and you can see some previous results. There was something very nice this year. And there is a separate line of research that I would like to mention concerning simple graphs. So no parallel edges, no weights, no parallel edges. Well, most of those results are randomized, and this sampling is really important. So for simple graphs, there was a breakthrough, and we have deterministic algorithms. So it would be nice to have something deterministic for general case, but this is not known. Okay, so if there are any questions, I'm happy to take them, or I can talk a bit more about the table and explain a bit more.
So are there any questions?
There's a question in the chat.
Yes. So the question is, can you provide any idea if we are dealing with K respecting cuts for larger constant K?
So that was not, this is not required for solving the minimum cut in this framework of Karger. We only have one respecting and two respecting. And if you move to three respecting, it's already hard. Maybe there is a way to solve this in M times log to power of K n, but I'm really not sure. Our method doesn't really generalize. So just for one respecting, there's a linear algorithm. It was given by Karger already, and for two respecting, now we have M log n. So maybe there is something that depends on the value of K, but we don't know that, and I'm not sure at the moment. I'm not sure.
Any additional questions?
I was also curious. So in particular, your algorithm implies something like n log² n for planar graphs. Is there anything known for planar graphs in particular that is faster than this?
I don't remember, but I think there was something faster, but I don't remember.
Yeah, it's n times log n for directed, undirected, weighted.
More questions, anyone? Okay.
So if there are no questions, maybe I could spend 1 minute mentioning some future work and open problems, if that's okay.
Yeah, it's 1 minute.
It's 1 minute. So the natural goal will be to get M log n, and I don't know, but maybe it's possible. So I don't see a reason for why you couldn't solve this two respecting problem in O of M time, although at the same time, I don't see how you could do that. So then you could stay within this framework by Karger and have M log n plus n times some power of log n because of the random sampling. So it's not clear how fast you can implement this random sampling. For M log² n, we were able to implement it at the same time. So maybe there is a way to achieve M log n plus n times log to some power. And again, the other open problem is to remove randomization. And for that, you have to come up with something completely different than this framework, because the first step in the framework is to do random sampling to find, to pack tree and then pack trees. So it's inherently randomized. So those papers use a different approach. So this is probably, that would be very nice, but that's probably very hard. We don't have anything of the form m times some power of log deterministically. So those are the two questions that I find very interesting. Okay.
Okay, there's another question in the chat. What about distributed min-cut algorithm? I can actually answer that if you'd like, but
yes, I don't know much about this case except that it's done in this paper, but I am not sure what's the results. If you could actually, if you could say, that would be very helpful.
There's a recent result that was uploaded to arXiv like a few weeks ago. So okay, so thank you very much. So now we're going to the next talk. Prantar, are you here?
Yeah, can you hear me?
Yes, great. Would you like to share a screen?
Yeah, sure.
Okay, so Prantar will tell us about graph coloring via degeneracy and streaming and other space-conscious models.
Do you see my screen?
Yes.
Okay. Yeah, so thanks for the introduction. These are joint work with Suman Beda and Amit Chakravarti. So in this work, we study the problem of vertex coloring. Here we need to assign colors to the vertices of a graph such that no two adjacent vertices get the same color. In doing so, our goal would be to optimize the number of colors. This is a fundamental problem in computer science with applications in numerous other problems. The problem of coloring a graph using delta plus 1 colors, where delta is the maximum degree of the graph, is a well-studied problem in this context. There is a very simple greedy algorithm for this, but it takes linear space and time and is inherently sequential. That's why several works have studied the problem in models with sublinear resources and in the distributed computing models, where this problem is challenging. In this work, our aim is to use fewer colors than delta plus 1, especially for certain sparse graphs. So we study coloring with respect to a different parameter called degeneracy of the graph, denoted by kappa. This is a good measure of the sparsity of the graph, and it is known that every graph can be colored with kappa plus 1 colors, which is more color efficient than delta plus 1, since kappa is always smaller and can be arbitrarily smaller than delta. In fact, in some real world graphs, we see that kappa is significantly smaller than delta. And so in this work, we try to find colorings using approximately kappa colors. We give kappa times 1 plus epsilon coloring algorithms in the data streaming and graph query models, and also in distributed computing models like MPC and congested Bleak. Thus, for a large class of graphs, including bounded degeneracy graphs, we use fewer colors than the corresponding delta plus 1 coloring algorithms. And at the same time, the other complexity parameters like space, time, number of rounds, they are the same or even better than the algorithms in the respective models. So we also have lower bound results showing that an optimal kappa plus 1 coloring is hard in these models. To be precise, it requires omega n squared space in the 1 per streaming setting and omega n squared queries in the graph query model. And in general, kappa plus lambda coloring algorithm requires n squared over lambda squared space and queries respectively. Note that these bounds hold even if the value of kappa is known to the algorithm in advance, but our upper bounds make no such assumptions. So to summarize, we initiated the study of degeneracy-based coloring in space-conscious models and gave colorings using approximately kappa colors, improving upon the number of colors for large classes of graphs. On the other hand, we showed that exact kappa plus 1 coloring has no sublinear algorithms, thus showing a gap between the complexities of kappa plus 1 and delta plus 1 colorings. Thank you for listening. I'd be happy to take questions now.
Thank you. Questions, please. How different is this from arboricity-based coloring?
This degeneracy parameters, kappa, it's between alpha and 2 alpha, where alpha is the arboricity of the graph. So you can think of this as order alpha coloring. But so kappa is a bit tighter than arboricity in terms of coloring, because there is always a 2 alpha coloring, where kappa is always known to be less than 2 alpha. So a kappa plus 1 coloring might be a bit tighter, but it's within 2 factor. So
Okay.
yeah.
Any more questions?
I think I saw in your set of results that you also have some results in a query model. And I'm wondering what your results there were. And I think this is you have some bound on the amount of queries that you can do there. But does this also take into what kind of queries are those? And do you also take into account like computation time in this model?
So the queries are paired queries, in the sense you query if there is an edge between 2 vertices, u and v, and the oracle returns you yes or no. And the other kind of queries is neighbor queries, that you query u and an index between 1 to n, that is with I, which you ask basically which is the ith neighbor of vertex u. So if you are given, if the oracle has an adjacency matrix representation of the graph, then these queries can be answered very fast, like in constant time.
Yeah, but in your model, the rest of the rest of after you do the queries, you have to do some computation. But this I guess is
correct. So yeah, after making the queries, we do a post processing. That post processing takes like order n polylog n time.
Additional questions?
So there was one question on Slack, but I mistakenly already answered it. But I'm happy to repeat the answer again.
Sure, go ahead.
So yeah, so the question was, have we done any experiments to show how better our algorithms are in practice? And to be honest, we haven't done any experiments yet, but we plan to do so in the future, given the simplicity of our algorithms.
Okay, thank you very much, Prantar.
Thank you.
Is Evie here?
Yes, I'm here.
Yes. Great. You can share your screen, please. Evie will tell us about proportionally fair clustering revisited.
All right, thank you. My name is Evie Micha, and this is joint work with my advisor, Nisaq Ham. It's about fairness in clustering. So if we consider the classic centroid clustering, okay, you have n data points, and we have invisible cluster centers, and our task is to open a set of k out of m cluster centers, and then to assign each data point to its closest cluster center. So we want that similar cluster centers, similar data points to belong to the same cluster. And Sen et al. In 2019 first introduced a notion of fairness with respect to proportionality. So here we assume that the n data points are human beings or are agents, and we consider that every group of n over k agents deserves its own cluster center or is entitled to choose its own cluster center. And specifically, they denote that the solution is proportionally fair if there is no group of size at least n over k, such that all of its members can agree and deviate to a cluster, to a feasible cluster center that does not belong in the current solution in order to reduce their distance. So here we see that the groups are not predefined, but every sufficient large group is entitled to choose its own cluster center if all of its members have incentives to deviate. And specifically, they saw that the proportional fair clustering does not always exist. And for this reason, they introduced an approximate definition. And specifically, they denote that the solution is rho proportionally fair if, again, there is no group of size at least n over k, such that all of its members can choose a different cluster center and all of them reduce their distance by a factor at least rho. So if does not exist such a group, then the solution is rho proportionally fair. And for this problem, they introduced an algorithm, namely greedy capture, for which they saw that for any metric space that we can imagine, it returns a 1 plus square root of 2 proportionally fair solution. So in our work, we focus in some very famous metric spaces, and in general, we consider that we are in the D-dimensional Euclidean space, where every point in the space is a feasible cluster center. And we saw that if we use the L2 norm in this asset metrics distance, then the grid capture returns a 2 proportionally fair solution. So here we see a significant improvement when we focus in a very famous metric space. While we saw that when again we are in the D-dimensional Euclidean space and every point is a feasible cluster center, but now we are using L1 norm or L infinity norm as a metric distance, then grid capture again returns an 1 plus square root of 2 proportional fair solution, and we have an example which cannot achieve something better. And moreover, we provide lower bounds for all these famous metric spaces. And I want to mention here that these lower bounds are not matched with the upper bounds from the grid capture. So there is an interesting open question here. And moreover, we saw that, as I said, the proportional fair solution does not always exist. And given an instance, it is then hard to answer if a solution exists for the, with respect to this instance. And there are some other results in our paper, and I don't have a lot of time to expand them now, but I encourage you to run through our paper if you're interested. And let me stop here. Thank you. And I'm happy to answer any question.
Thank you. We have time for questions. Anyone? So maybe you've said this, but what did the lower bounds give with respect to the upper bounds?
No, I didn't mention that. So for the, especially when we are in the L2 norm, when we use L2 norm in the metric space, the lower bound that we have is 1.15, while for the L1 and N infinity, our lower bound is 1.4, while grid capture returns a 1 plus square root of 2 proportional fair solution. So there are significant gaps there.
Which direction do you believe is correct?
So in our paper, we have another model that I didn't include it in this short presentation. So we consider the metric space in which we have graphs too. So there we assume that we have a graph. Every vertex is a feasible cluster center and it's a data point concurrently. And we assume that the edges have weight equal to 1. And we saw for some special cases, for example, when the graph is a tree, a proportionally fair solution always exists. While we don't answer this question for general graphs. So for me, this is the most interesting question. I'm not very optimistic how someone can close the gaps between the lower and the upper bounds when we are looking at the D-dimensional Euclidean space. But I think it's very interesting when we are talking about graphs, and especially if we consider this problem in applications like facility location, in which we have agents and we want to build a public facility, and we try somehow to satisfy all the agents. And I think that this kind of definition of fairness makes more sense when we're talking about facility location.
Sorry, I'm muted. There's a question on the chat. Does the problem simplify much if we constrain the feasible cluster centers to some smaller subset of points in Euclidean space?
So I'm not sure that if we constrain the sizes of the clusters is the question.
If we can constrain the feasible cluster centers to some smaller subset of points.
Okay, yeah. So in the previous work, as I said, the results are for any metric space. So here, when we have, when they Senetal defined that we have infeasible cluster centers, M can be a finite set. It's not necessary to be the whole space. And for these specific cases, we have this 1 plus square root of 2 lower bound for which there are upper bounds, sorry, for which we have some much lower bounds. Some example in which grid capture cannot return a better solution. And I think that the improvement that we have when we are looking at the L2 norm is exactly because we assume that the whole space is a feasible cluster center.
Any additional questions?
I was also curious about your results on graphs because I thought this was very interesting. So I think you proved that there always exists such a fair clustering when the graph is a tree. If the graph were to look close, is close like a tree, it's almost a tree. It has maybe a few additional edges, or maybe even if it has bounded tree width. Do you think that something like this could still exist?
Probably my intuition is that it always exists, a proportionally fair solution in graphs. We really tried hard to find an example in which that does not exist, but we didn't find. But we don't have a proof in which we saw that always exists. But my intuition is that always exists a fair solution in graphs. So especially we saw that when we want to place at least n/2, when we have a connected graph and we want to place at least n/2 physical classes centers, then again, always a proportional fair solution exists. So the gap here is when we have cycles, so we're not talking about a tree, and we want to place less than n/2 centers in the graph. So this is unknown, and probably if someone starts looking at some graphs that are very close to trees, which is with exception of some of the edges, probably this is a very nice direction to start.
Yeah, because I guess for just a cycle, it should be possible.
Right, for a cycle, or if we have a line, yeah, a line is a tree. Yeah, for a cycle, it's possible. That's true. So probably if we take some cycles that are connected like a tree, yeah, that's
yeah. So true. Like a cactus graph or something like that, where you have cycles that are connected at vertices, such that the cycles form like a tree-like structure. This type of structure that should follow without too much issue, then maybe.
Yeah, I suppose that our algorithm can be adjusted for this kind of graphs. This is my intuition, but yeah, this is a very nice question. Thank you.
All right, thank you.
Additional questions? Okay, thank you very much, Evie.
Thank you very much.
And our last speaker is Randuan. Ran, are you here? I think he is here. Ran, can you unmute yourself?
Yes, okay.
You can feel free to share your screen, and Ran will tell us about round-trip spanners with 2k-1 stretch.
Okay, the title of our paper is Roundtrip Spanners with 2k-1 stretch, and I'm Randuan, and this is the joint work from with Ruoxu Chen and Yonggu, all from Tsinghua University. So here, spanner is for graph G, it's a spanning subgraph of G, in which it is sparse, and it can preserve approximate distances pairwise. So a spanning tree is just like a spanning subgraph that only preserves connectivity. But now we want that it preserves approximate distances. And because a spanner is a subgraph of G, the distance in it can only increase. But we hope that it doesn't increase a lot. Okay, so we call a spanner S with stretch T. That is for every pair of U and V in the graph G, the approximate distance in the distance in the spanner is at most T times the original distance in the graph G. So in undirected graph, we have a 2k-1 stretch spanner with all n to the 1 plus 1 over k edges. This is a classic result. And this the trade-off between the stretch and the size of the spanner is tied by Erdos-Gers conjecture. So here we can see the n is the number of vertices. But in directed graphs, we can see if we just consider the distance, that is from every distance, every vertex to another, then of course there's no non-trivial spanners. Right? Because we can construct such a bipartite graph, complete bipartite graph, and all edges are from one side to the other side. But to delete any edge will cause that this edge cannot reach this vertex cannot reach this vertex. So there's no non-trivial spanners. So in directed graph, we consider round-trip spanners instead. Round-trip spanner is that from U to V, which first from U to V and then from V to U. We need to travel back. Or equivalently, it's the shortest cycle, which goes through both U and V. Okay, so it also satisfies the triangle inequality. So this is a summary of the results on round-trip spanners. So previously, there are 2k plus epsilon stretch spanner with size about like k times n to the 1 plus 1 over k times log and w. Here, w is that we assume that all the edge weights are real numbers between 1 and w. Also, previously there are a strongly polynomial size that it doesn't depend on w. So in this paper, we improve the stretch to 2k-1, and the size is also k times n to the 1 plus 1 over k times log n. So it can also be independent of w. So this is just closer to the lower bound. And our contraction time is like omega OMN. Of course, there are many round-trip spanners with faster contraction time than that. We stretch a little bit larger, but contraction time can be subcubic. So I think a very good future direction is that we improve the contraction time of such round-trip spanners. Okay. So any questions?
Thank you. Any questions? So just to make sure, are these weighted or non-weighted?
Weighted, okay.
Right.
Weighted, so the edge weight can be between the 1 and w.
Okay.
Are there any lower bounds for round-trip spanners?
Yes, I think that means that the lower bound for this better.
Yeah, sure.
That's conjecture.
More questions? Okay, so I think this wraps up this session. Thank you to all the speakers and all the participants. See you in one of the next sessions. Bye-bye.